All right, folks, next video. So we're going to get into stuff that I think is universally interesting, right? So as you can see here, like the biological effects of radioactivity. So let's get into that. I got to put the music away because it's going to distract me. Okay. So as I said, stuff that I think is good to know to create a better informed citizenry, such as the biological effects of radioactivity. Okay. So the main effect that radiation exposure has on your body is what we call ionizing radiation. Okay. And so here I'm showing you this process of water being ionized into H2O plus and releasing an electron. And that takes an enormous amount of energy, 1,216 kilojoules per mole. And so why is that the main effect? Well, because the majority of the mass of your body is water. That's what's going to absorb the brunt of that ionizing radiation. And that can be alpha particles, beta particles, gamma, any of these types of radioactive particles can induce ionization of water. And once that happens, you can see then the second reaction takes place. So this is the mechanism for ionizing radiation. So now we got H2O plus reacts with an ordinary water. That becomes H3O plus. But now, because an electron was kicked out, we've made an OH radical. So that is a free radical. Okay, that is not hydroxide. So I'm going to write OH minus, and I'm going to put an X through it. If it was just hydroxide, no big deal. Okay, but this is the hydroxyl radical. And if you've heard people talking about, free radicals in your body and how you want to consume foods that fight free radicals, this is exactly what you're fighting. Okay, these OH radicals are extremely reactive, and they will just chew apart things in your body. So it'll chew apart your DNA as well as other important things in your body. Okay. And so certainly there is a natural production of free radicals in your body. And this is why, there's a whole line of consumer products that are meant to fight that. But when you take a heavy dose of radiation, you're going to get a huge production of OH radicals in your body, and that's going to cause lots and lots of damage. Okay. So the amount of ionizing energy you absorb is expressed in either grays or rads. And maybe you've heard of a rad before. So a gray is 1 joule of ionizing radiation per kilogram of body mass. Okay, so let's write body mass. So if you get exposed to 10 grays, you're talking about 10 joules per kilogram of your body mass. Okay, so there actually might be a lot more ionizing radiation that you're actually exposed to. But these are scaled to be per kilogram of exposure to your body. Okay, so now the rad is very similar to the gray, but it's just 1/100th of a gray. And so if you have large ionization energy exposures, you would express that in rads. Okay? So on the other hand, so that's how much energy you're exposed to, but that doesn't express how much tissue damage you might experience. Okay, so those are given as sieverts or rems. Okay, so 1 sievert is a gray, so that's a joule per kilogram of body mass, times what's called the relative biological effect. Okay, so let's write that down. Relative biological effect. Okay, and so those RBEs are expressed here. And so what you can see now, the amount of tissue damage you're going to have is actually dependent upon what type of radiation you're exposed to. So as you can see, gamma and beta have the smallest RBE values, indicating that they would give you the least amount of tissue damage, whereas alpha particles or even protons, right, are way up there, a factor of 20. So if you're exposed to the same amount of ionizing energy, there's 20 times more damage that could happen with an alpha particle versus a gamma ray. However, there's a caveat there, okay? And that's the following. So if you are exposed to alpha particles and you're wearing clothes, you really have nothing to worry about because alpha particles are so big and massive, they can be stopped by a piece of paper, okay? So alpha particles give you the least amount of tissue damage outside of your body. However, if you ingested a material that gave off alpha particles, they would cause the most amount of damage inside your body because now you don't have like a protective layer. And I mean, literally your clothes can protect you from alpha particles. And if you were doing stuff with alpha particles, you would likely have a full body suit on, right, to protect yourself. But it doesn't have to be lead lined or aluminum aligned, right? Just a thin layer of clothing will stop alpha particles. But as I said, if you ingest alpha particles, you're going to have 20 times more relative tissue damage internally than you would for, let's say, a gamma particle. Okay. So now, but if we continue along this, you can see a beta particle would pass right through your clothing, okay, and damage your tissue, right? But a beta particle could be stopped with a relatively thin piece of aluminum, 5 millimeters. That's a little bit less than 1/4 of an inch, okay? And so if you go back to the RBE value, beta particles are quite low in their RBE value. So if you were to ingest beta particles compared to alpha particles, the beta particles would give you far less internal damage. However, your clothes or a piece of paper are not going to protect you from beta particles as effectively as an alpha particle. So hopefully that makes sense, okay? And now if we look at gamma, gamma can pose the most amount of risk for external exposure because you notice here a gamma particle, it's small, it's a photon, okay? It's light, so I'll write that down. It doesn't have any mass. It passes right through paper, right through aluminum, and you have to use a fairly thick lead block to block a gamma ray, okay? And similarly, if we had X-ray exposure, which is just a little bit less energetic than gamma, it's the same thing. And this is why when you go to the dentist office or you get an X-ray done, you broke a bone or something like that, you wear that heavy lined lead jacket to protect your vital organs because those gamma rays will pass right through and could get internal, right? It could cause internal tissue damage unless, of course, you have a big, heavy lead apron protecting your vital organs, okay? So if you're getting, a little X-ray in your mouth or like your arm, a small amount of exposure is not that big of a deal. But all the same, you do want to protect your vital organs from these types of radiation, especially gamma or X-rays, okay? So here are some dosimetry effects from ionizing radiation. And so again, this is in units of sieverts. And I'll just remind you, sievert is, the amount of ionizing energy that your body absorbs times this relative biological effect, okay? So again, it depends, what type of particles you're being exposed to. But all the same, if we kind of look at the scales here, so if you look at here, if we're down to 0.05 to 0.25 sieverts, no acute effect, possible carcinogenic or mutagenic damage to DNA. So that would be like the slow killer, right? If you start having some mutagenic damage to your DNA, you might not notice that right away. And years later, it comes up, okay? So now I'll just remind you, a typical X-ray dose that you get from the dentist office is 1, 2, 3, 4, 5. So that's 50 microsieverts. So when you're exposed to X-rays, at the dentist or at the doctor's office, you are not going to have to worry about mutagenic damage to your DNA. Okay. However, if you get a bigger dose, so 0.25 to 1 or even 1 to 2, so you will get a temporary reduction in white blood cell count. And between 1 to 2 sieverts, this is where radiation sickness kicks in. Okay, and it comes in fast. So if you go above that, 2 to 4, that's called severe radiation sickness, which, of course, is even worse than this 1 to 2 level. And then if you unfortunately are exposed between 4 and 10 or even above 10, that's game over. That's unfortunate for that type of exposure. Okay. And so now what I want to point out, a typical dose for cancer radiation therapy is about 60 to 80 sieverts per round. So that is intense. And so if you're thinking, well, why don't people die from that? It's because it's focused on a really narrow spot in your body. Okay, so these, you notice here, these are acute effects of whole body dosages, right? So with this, like 10 sieverts, death within hours, you'd actually have to be exposed to a huge amount of grays or rads, right? A huge dose to get your whole body mass exposed to that level. So for cancer radiation therapy, it's a very, small area in your body. However, if you unfortunately have known people that have had to go through this, then you get really sick from getting cancer radiation therapy. Okay, it has other unwanted effects besides just killing the cancer, such as all of the things listed here. So it is not pleasant. Okay, and so the book talks about lots of ways that we are exposed to radiation just naturally. So when you get up on an airplane, you're actually exposed to some cosmic rays and some of the remains of nuclear material from all the atomic explosions we've done. So you do have a slight increase in radiation exposure. Of course, when you go to the dentist, you get a slight radiation exposure. Okay, but it's all what we would consider to be background. And so I would encourage you to actually read this section in the book because they talk about the Chernobyl accident and they also in what is now Ukraine. And they also talk about the Fukushima meltdown that occurred in Japan in 2011. So I would encourage you to read that. There's some really good information about what happened to the world and to the folks there with respect to radiation exposure. Okay, folks, so that's all I'm going to talk about biological effects of radioactivity. We could obviously make a whole week out of this discussion, but if you're still interested in this, I would encourage you to read some more about it. All right, I'll see you in the next video.